Hello students, this is our next lecture on the theorem of parallel axis. So in previous lecture we have studied what is moment of inertia, physical significance of moment of inertia, as well as formula derivation of moment of inertia of various shapes, that is moment of inertia of disk and moment of inertia of ring. So what is the necessity for the derivation of theorem of parallel axis, or what is the use of this theorem of parallel axis, theorem of perpendicular axis? So see, in your textbook at the last there is table number 3. So in this table you can get the various moment of inertia of all uh, the shapes about symmetrical axis, about symmetrical axis. Symmetrical axis means what? If you uh, possess, or if you consider this ring and the axis is passing through its symmetry, that is around this axis, the mass of that body, or the this body is symmetrical about this axis. So this is the axis of symmetry. So again, if you consider a disc like structure and axis is passing through its center, then it is said to be symmetrical axis. But this kind of moment of inertias are find by a mathematical integration method. Okay, we use integration and find the moment of inertias of these bodies. But what about bodies of different, or uh, different symmetrical axis, or different axis of rotation? So if axis of rotation is passing, this is ring, and axis of rotation is passing through its plane and parallel to its diameter, any of its diameter, this is axis of rotation. So this axis of rotation is perpendicular to the axis of symmetry. Okay, then in this case we have to use the different perpendicular theorem for perpendicular axis. And if you consider there is a rod uh, at the center of mass, the axis is present, that axis is known as axis of symmetry. And if we consider that rod performing a rotational motion about a axis passing through its one of the end. Okay, so if this rod perform a rotational motion about this axis which is passing through its uh, one of the end, so this axis is parallel to central axis of symmetry. So in this case we are not, or we are not available the this in mathematical integration tool for the calculation of moment of inertia. So in this case we use parallel axis theorem. Okay, if the axis is axis of rotation is parallel to the axis of symmetry, then we use theorem of parallel axis. If axis of rotation is perpendicular to the axis of symmetry, we use perpendicular axis theorem. So let us see one by one what are the parallel axis theorem and perpendicular axis theorem. So see, what is theorem of parallel axis? So after solving the derivation, or derive an expression for a moment of inertia of a body with a parallel axis, we get this relation, that is IO equal to IC plus mh square. Here IO is nothing but the moment of inertia of this rigid body. This is the rigid body about a axis passing through the point O. Suppose this is point O, again, which is equal to moment of inertia of that same body about an axis passing through its center of mass, that is C point. Suppose that C point is lying here. Okay, plus m is a, capital M is a mass of that body, and h is a perpendicular distance between point O and C. So this is perpendicular distance h. Now see how the theorem is proved. So consider for the proof of this theorem, parallel axis theorem, we have to consider two parallel axes. One is passing through the point O and another is passing through center of mass point of that body. So this C is the center of mass of that body. Center of mass is nothing but the point in that body at which whole mass of body is concentrated. So mass distribution about that point is uh, done so that the whole mass of that body is supposed to be concentrated at a point. Such a point is called as a center of mass point. So C is the center of mass point, and suppose the moment of inertia of this body about an axis M O, and suppose this is point P, and suppose this is A C and M axis. So M is here. So the axis is AC and B axis. So we have two axes. First is a MOP axis, another is a ACB axis, and distance between them is h. Now consider a small point mass which has a small element. It is a small element of mass dm which is located at a point. Suppose here D is a point at which the small element is located, and if I draw this dotted line from O to D, again C to D, okay, now we have to draw a perpendicular on OC. I have to reproduce OC here, so this is right angle triangle, and I give the name N for this point. Okay, so this is the construction of our theorem.